Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors Chapter 10 Quiz 2 Review Solutions on Trigonometric Ratios and Functions, Part 2. This one focuses on graphing trig functions, identities, and also solving trigonometric equations. For this problem, let's check out the transformations that are happening. So we have a -4 outside the function. The negative gives us a vertical reflection. The 4 gives us a vertical stretch. And then this minus pi over 2 inside the function is giving us a translation of right pi over 2. So vertical reflection and stretch, and translation right pi over 2. All right, let's do our parent table for sine of x. So we've got from 0 to 2 pi, we've got 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. And now to incorporate these changes in the g of x function that we're using to actually graph this, for the x's, since we're going right by pi over 2, we have to do x plus pi over 2. And then for the y's, to get both the reflection and the stretch, we need to multiply -4 by the y values. All right, let's add pi over 2 to all the x values first. So 0 plus that just gives us pi over 2. Pi over 2 plus pi over 2 is 2 pi over 2, or just pi. And then pi plus pi over 2 is 3 pi over 2. 3 pi over 2 plus a pi over 2 is going to give us 2 pi, or 4 pi over 2. And this is 4 pi over 2 right here, plus another pi over 2 for 5 pi over 2. Now for the y values, multiplying by -4, we've got 0 is going to just still be 0. And then 1 becomes -4. Then we have 0, +4, and 0. So to get all this on a graph, I'm going to go by pi over 2's, starting at 0 and ending at 3 pi. That should help me get everything I need in the middle here for the x values. For the y values, I'm going to go from -6 to 6. That'll let me get these 4's in here. So our first point is pi over 2, 0. It's okay that that's not on the y-axis. Then we've got pi, -4, 3 pi over 2, 0, 2 pi, +4, and 5 pi over 2, 0. And going through our dots here, this is our piece of the sine wave. To graph this function, 2 cotan of pi over 2x, let's look at the transformations first. So we've got the 2 out here giving us a vertical stretch. The pi over 2 in here, well, let me think here. Pi over 2, that's like 1.7 or something. That's bigger than 1. So that's going to be a horizontal shrink. All right, so vertical stretch, horizontal shrink. Let's write our parent table for cotan. So going from 0 to pi, we've got 0 and an asymptote there originally. Pi over 4 and 1. Pi over 2, 0. 3 pi over 2, -1, and pi with another asymptote, undefined kind of spot there. So to modify all this for the g function, the pi over 2 inside here means we have to multiply the x values by 2 over pi, the reciprocal of that. And then for the 2 outside the function, we're going to do 2y to incorporate that vertical stretch. So let's do the x values first. 2 pi over 0 is just 0, so that's nice. 2 pi times pi over 4. Pi's are going to cancel. We've got 2 over 4, which is 1/2. And next, 2 pi times pi over 2. Well, those are literally reciprocals, so that's just 1. 2 pi times 3 pi over 4. Pi's cancel again. We've got 6 over 4, which we'll do as 3/2. And then we've got 2 over pi times pi. Pi's cancel, so that's just 2. Now for the y's, multiplying these by 2, undefined is still undefined. 1 becomes 2, then we got 0, -2, and undefined. So to fit all this on my graph, I'm going to make my x values go by 1/2, and my y values can go by 1's. Let's graph all this now. So at 0, we have a vertical asymptote. That's what this undefined means. So I can just do a dashed line there if I want. I don't really need to, though, because the y-axis already gives us a guideline to approach. And then we have 1/2, 2 right here, 1, 0, 1.5 or 3/2, -2. and at 2 we have a vertical asymptote that we do need to draw. So I'm just going to approach the asymptotes and go through the points. So here is my cotan curve, just one period. On this problem, we have two people swinging jump ropes. The highest and lowest points of the middle of each rope are 80 inches and 2 inches. Each rope makes 2 revolutions per second. They want a model for the height in inches, so that's h, of one of the ropes as a function of time, t, which is in seconds, given that the rope is at its highest point when time equals 0. All right, so to write this is going to be a trigonometric model because the height of the rope just keeps cycling between 2 and 80 as the rope goes round and round. So I know that I'm going to need a few things. I need my amplitude, my A value, my B value. I also need an H and a K. So let's get each of those. For the A value, the amplitude, I need half the height. That's the amount of fluctuation. So that's going to be 80 minus 2 to get the height, and then divide that by 2. 78 over 2 is 39. And then for the B value, before I can get that, I need the period. And they didn't give me the period. They didn't tell me how long it takes the jump rope to do a full cycle. They gave me the frequency instead. They said it was 2 revolutions per second. So if I take the reciprocal of that, I figure out how long it takes to do 1 revolution. So if our frequency is 2, our period then is going to be 1 over 2. And to get the B value, the horizontal stretch factor from the period, we have to do 2 pi divided by the period. So 2 pi divided by 1/2. Same change flip, that's really 2 pi times 2 over 1, which is 4 pi. So that's our B value that makes it into our formula. I'm going to do the K value next. So that is the midline, the vertical shift. That's going to be the average of the highest and lowest points. So 80 plus 2 over 2. 82 over 2 gives us 41. And now for the H value, so that's going to be where the cycle starts for the trig function that we're choosing. Now the easiest way to do this problem, since they told us the rope is at its highest point at time 0, they're basically saying we're at the top of the wave on the y-axis, or I guess this would be the h-axis. So cosine likes to start at the top of the wave at x equals 0. So if we use an h value of 0, we can use the cosine function, the positive cosine function. So for positive cosine, we can use h equals 0. Okay, now just a few other kind of ways of thinking about this. If we had different points that the jump rope was at, just to get you a full review, if we were at the lowest point at time 0, then you'd want negative cosine because that starts at the bottom of the wave. And if you were at the rope was at its like middle point going up, that would be positive sine. Middle point going down would be negative sine, all at time 0. In any case, our formula we're going to use, we're going to do A positive cosine B x minus h plus k, and we'll use h and t instead of y and x, but same idea. So we can write h of t equals the a value 39. We've got cosine and the b value of 4 pi. H is 0, so we just have t minus 0, or just t, plus our k value we found of 41. So this all together, 39 cosine 4 pi t plus 41, that is our h function. On this problem, they want us to simplify this, which means that we want a single number or trig expression, and we don't want any reciprocals, and we don't want any weird funny business inside the trig function like this negative x here. So there's a few things we can do here, a few identities we can use to help us out. So first thing I always try to figure out is if there's weird angles, and this is part of my APAC, AP, AC sort of toolbox. So we have angle identities that we try first, then Pythagoreans if you have squared trig functions. A stands for algebra if you need to factor or FOIL or anything or multiply things out. Also splitting up fractions. And finally the C is just turning everything into cosine and sine, which usually will get you there eventually, but it is the longest thing. Now one thing that we have to do first on this problem, since we have a negative angle, we're going to use our negative angle identity. There's 6 of them depending on your trig function. The relevant one here is that secant of negative x equals secant of x. And it's related to the cosine of negative x equaling just cosine of x. It's an even function. So we can rewrite this as just secant of positive x. Now for the squared trig functions down here, we can do something with those as well. There's a Pythagorean identity. It's one of the big 3. So this one is cotan squared plus 1 equals cosecant squared. There's also, you might recall, tan squared plus 1 equals secant squared, and sine squared plus cosine squared equals 1. So they're all useful in different situations. Make sure you've got all those memorized or written down. So in this case, to match this negative cotan squared plus cosecant squared pattern, in this identity I could just subtract cotan squared over to the other side, and that would give me basically all this. And then I'd have 1 left over on the left side. So all of this stuff then is just equivalent to this 1 that would be left over. So I can replace this whole thing with 1, and then just simplifying that fully, we have secant of x. For this problem, we are given cosine of a, sine of a, and sine of some other angle b, and we're told that angle b falls between 0 and pi over 2. Based off that, we want to find the sine of a minus b. So there's a sine of a difference angle identity that uses all the information they gave us. It also requires sine of, or cosine of b though. You need the sine and the cosine of a and the sine and the cosine of b for this whole formula to work. So we're going to start by finding cosine of b based on what we've got here. Now the key for this one is that since b is between 0 and pi over 2, that means we are in quadrant 1. This is 0 degrees to 90 degrees. So the x and the y values there are positive, which we do need to keep track of because if they're negative, then that's going to change our final answer when we figure these things out and plug things in. So at this point, I have to figure out if I'm going to get cosine of b in general is x over r. I have an r value from this sine, but I'm going to need an x value. So I'm going to need my Pythagorean theorem to get all that. So let me start by writing down what I have. Since sine of b in general is y over r, and we know that y is positive, that means that we have a positive 12 for y, and an r value, which r is always positive, of positive 13. Now to get the missing x value that I need for the cosine, I'm going to use Pythagorean theorem. So x is going to be the square root of r squared minus y squared, or 13 squared minus 12 squared in this case. This is 169 minus 144, which is 25, and the square root of 25 is 5. So there's our x value. So cosine of b is going to be x over r, as we said. So that means we're going to have 5 over 13 for that. All right, so let me write out my sine of a difference formula. That's going to be sine of a cosine of b minus sine of b cosine of a. And now plugging all the different pieces in here, sine of a, they gave us that was 3/5. Cosine of b, we just found, that's 5/13. Minus sine of b they gave us, that was 12/13. And cosine of a was over here, that was negative 4/5. Simplifying a bit, we've got 15 over 65 over here. You could reduce this, but since you're going to need a common denominator, you should probably leave it unreduced until you combine these together. So 15 over 65 for the moment. And then over here, this is going to be a positive 48 over 65. Adding these numerators together, we've got, let's see here, that's going to be 63 over 65, which I can't reduce any further, so this is my final answer. For this problem, we're trying to solve this trigonometric equation for all the angles from 0 to 2 pi. So we're going to start by isolating our trig function. I can do that by just dividing by -2. So we have sine of theta equals negative radical 3 over 2. Next up, I'm going to go ahead and graph this on the unit circle. Since we have sine equals a number, they're telling us that the y value equals a number. Remember, sine is y, cosine is x, and tan is m, the slope. So we're asking, where does the y value equal negative radical 3 over 2? Well, I'm not sure exactly where, but I know this is going to be a negative number between 0 and negative 1. So we're going to be down here below the x-axis. So we've got one spot that's going to be somewhere over here, and we have another spot that's going to be somewhere over here. These are both where the y value is this negative radical 3 over 2. And I'm not being super precise, it's just down there somewhere. So the thing that I really want to do, though, is figure out what quadrants I'm in for my answers. So we've got quadrants 3 and 4. So I'm going to figure out a reference angle based off of this, and then I'm going to use that along with knowing which quadrants I'm in to actually get my exact answers. So for my reference angle, I have to do a reverse lookup in that special angle value table where you might have that memorized. And I'm only working with the positive version of this radical 3 over 2 because I'm just getting a reference angle, not the exact answer. So I'm asking myself, sine of what angle equals radical 3 over 2? Well, you might remember that that's sine of 60. So 60 is my theta prime, my reference angle for this problem. So to get these answers, I have to start at the nearest x-axis and move 60 degrees into these two quadrants. So for quadrant 3, I have to start at the 180 line and move 60 degrees forward to get here. So 180 plus 60 is going to give me 240 degrees down here. And now for quadrant 4, I have to start over here at 360 and go 60 degrees backwards to get down here. So that's going to be 360 minus 60, which is 300. And I do need to convert these into radians because that's what they asked for with this range here. So we've got 240 pi over 180. I can reduce that by 60s to get 4 pi over 3. And 300 pi over 180 reduces by 60 as well to get 5 pi over 3. So those are my two final answers.